Hello, everybody, and welcome to this installment of the Royal Tyrrell Museum's speaker series. First, a short introduction about our speaker today, Dr. Elena Ghezzo. She studied a BSc in Natural Science at the University of Padua, mostly interested in museum exhibitions and the management of zoological heritage. This was followed by a master's in prehistoric science at the University of Ferrara, which involved a study on carnivoran accumulation in a Middle Pleistocene cave near Verona. Her PhD was done at the University of Florence at the Earth Science Department, which involved an attempt to relocate fossils to their original position within a cave deposit that had been excavated more than 100 years earlier. And at this point, Elena had her first contact with GIS techniques and spatial coordinates. This also involves some work with European leopard, which used to live in Europe more than 400,000 years ago. Now, basically, her interest in good practices for fossil management increased over time, and she did a second master's at the University of Padua in GIS and unmanned aircraft systems. So she has a drone license, was introduced to satellites and analysis of multispectral images, which has been developed in her current Marie Curie project, and this will be covered in the presentation. She's just moved back to Italy after spending 2 years at the University of Oregon as part of the Marie Curie project. And this time, of course, was partially fragmented due to field expeditions, the pandemic, and a baby. In the next few months, she'll be developing collaborations to study her original love, which is felids, in collaboration with the National Museum of Scotland. So she should be in my old patch of Edinburgh over the summer and in some US institutions such as LA. So with that, I'll hand over to Elena.
Thank you, everybody, for being here today. And let's go straight to the main topic of this presentation, or close to that. So first of all, I'm going to a brief introduction of what is the techniques and the cluster classification I'm using for run analysis over satellite images that covers large portion of land. And then I will show you some examples where I actually run the classification and see what is the result for them. Basically, the idea of matching satellite images with my main field of expertise is not very new. Other researchers, before I started the Marie Curie project, they tried to locate outcrops, so potential fossiliferous outcrops, where to find fossils. They didn't run classification or analysis to find actual real specimens on the ground, because some of them were working before we had enough resolution to analyze the ground on detail, and and some others analyzed outcrops that were not really paleontological, but paleoarchaeological, for example. So when I first started my project, there were three main questions on my brain. The first one was, are there satellites with enough resolution on the ground to be able to really see the fossils? And the second one, are there localities where I can test the method? Or is just a unique locality here and there, and is not a topic that can be interesting for the scientific community? The second main question was, is that really possible to distinguish a fossil from the matrix, from the background where the fossil is exposed? So in order to answer this main question, I proposed to the European Commission the REFINE project, and that was supported, that passed the selection, and I obtained a Marie Curie Global Fellowship. That means I had the opportunity to spend 2 years out of Europe to learn some good practices and some method and advanced mathematical and statistical tools. And now I'm back in Italy, as Jeff just said, to transmit my skills, my new skills, and hopefully publish some papers. When I first started to think about the project, I tried to resume all the goals I wanted to reach during the 3 years in a main question. And the main question was, how can we find new fossils? Usually, you probably know that the fossils, the new localities that are discovered day by day, are reported from casuality, from people just walking on a path and discovering a new place, a new amazing fossil. And that's great. But maybe we can try to standardize our knowledge of the field in advance in order to improve the effectiveness and reduce cost and risk related to fieldworks. So part of my project was answering this main question through the analysis of the satellite images. The other part, but this is another story, is to consider the distribution of extinct species. But this is another story. Today we are focusing on satellite imaging and the information we can extract from those images. First of all, why to analyze satellite images and why specifically for sea fossils from our office? Well, today it's an easy answer because with the pandemic, we cannot really travel abroad, and specifically in remote regions, it's very difficult. But in general, we need to improve the effectiveness and mainly avoid that these fossils are taken and moved to the black market. I'm going to show you several examples and try to explain main concepts through photos and my main experience. So this is me before two fieldworks, the ones before and during the fieldworks. The one on your left is I was in Oregon moving all those stuff to Peru to do fieldworks there. Those include 6 baggages, including a sleeping bag, a tent that I didn't use because it was too big, and in Peru it was too windy to build and sleep within the tent, but I didn't know that. And I moved there the drone and all the legal documents related to the possibility to move a drone from one country to another. There are some restrictions. I also had 2 solar panels and all the tools and goods I need for fieldwork. The second photo is me in the desert in Eritrea. And as you can probably see, there is a straw coming out from my backpack. That straw is connected to a bag with 5 liters of water, and I needed to sip pretty frequently to avoid to be hydrated throughout the walking through the field. I'm not telling that doing field works is not, I don't enjoy doing the field work because I think it's probably the most amazing thing you can do being a paleontologist. But you have to be prepared. And it is better if you know in advance. The more information you have in advance about the field, about what you are dealing with, the most effective will be your results. Regarding the black market, you can just Google it, and you see thousands of examples of fossils that are stolen or that are removed from the original locality. And this is not just a loss of information regarding the specimen per se, but you are also, as you probably know, losing the information of the context. So what kind of other species were related to that specific specimen that is lost. And obviously they are in private collection and we cannot have a control of them. And no other researchers can have access to them. And this is a big deal. And of course, nowadays it's very important, and we have the tools to try to control the region from our office, from our home. Examples of black market of fossils removed from the original locality and moved to the black market are, for example, dinosaurs from Mongolia and Argentina, but also shells and reptiles from North Africa. And also in the United States, we have some examples in national parks, like in the ones in Utah and in Arizona. There are localities with fossils that have specific characteristics that allows you to try a classification from a satellite. And those localities are more or less everywhere on the world. I'm going to focus my attention on three of those that are the petrified forest and the Pisco Basin and Wadi El Hitan, but we have other fossil logs in Yellowstone and, for example, dinosaurs in Niger. Now, let's go to the second question. What can we see from out of the atmosphere? So what kind of images, what kind of view can we have from a satellite? So we have to have in mind that different satellites has camera for different purposes. And I'm going to share with you some examples again. So probably you recognize this photo, this picture. This was taken in February 2021 from a satellite looking not at the Earth, but looking on Mars. And he was capturing the Perseverance rover landing on the Jezero crater. That's an amazing photo because it is taken from 300 kilometers of altitude over the planet, and it reached 30 centimeters of resolution. It is a black and white photo, but you can really see a lot of the details that are on the ground. Another pictures was taken 1 month later. This was an unfortunate event when a vessel, the Evergreen vessel, was blocking the Suez Canal for over 6 days. Probably you read all those examples in the newspapers. And why I'm showing you these pictures, this example, because you see the two imageries are taken with a different angle. And one of the two is taken in panchromatic, the one on your left, and the other one is a multispectral image. We will see shortly what does it mean. But you can see they have different angle and a different resolution. The ones on your right is kind of, you can feel the details better than the one on your left. Another sad example, again, is with the satellite images. You can monitor the land through time. You know that. This is a familiar concept. And this is just an outstanding and impressive example of the same region in the Amazon forest in 10 years. This is the last example, just to have you into the idea of different kind of information you can have from the space. So this is a photo taken from the International Space Station, and I'm actually at the red dot you can see on the top of the images, and that image is part of a project that is called the Gateway to Astronaut Photography to Earth, and it is devoted to control and to monitor the evolution of the vegetation under the lagoon. You can see the greenish, brownish colors on the left of the images. As you probably know, the lagoon is very sensitive to climatic change. So this was a big project, is still going on to monitor the lagoon and the vegetation that is very peculiar for the region. Those examples has nothing to do with fossils, but maybe not. Maybe yes, they have a relation with fossils. And all we have to have in mind that all those images have difference regarding to colors, resolution, angle, and clearness. But those images were created by cameras that were assembled to target very different objects. The atmosphere, so cloud, curvature, or very sensitive to the detail on the ground, or they were like collecting information out of the visible light. Okay, let's spend some words about Google Earth. So a lot of satellite images are available for free online. You can search for them, and you can download them and analyze them. Some of them has better resolution than others, and the most known platform where you can see the ground from satellite and you can navigate it is Google Earth. Why I am not using Google Earth for running my classification? Well, it's clear from these pictures. Even though Google Earth can reach higher resolution, the way Google Earth is matching the imageries can create some aberrant features, objects, like this cruise that is basically a ghost leaving the port. I'm not using Google Earth for the exact purpose of classification. I'm using Google Earth to verify the outcomes from my classification. Okay, now that we have this in mind, we can dig a little bit in detail of what kind of information are behind the images. Those are beautiful images, but they are organized in a way that is useful for different purposes. So in my project, I had to select the ones that has the characteristics I could use for run my analysis, obviously. So the basic concept here is several bands has best outcomes. What does it mean? So this is a multispectral camera. Don't be scared. It's a basic camera. It's basically different cameras put together, compact together, and they are recording information from exactly the same scene. The difference within each of the lenses you can see that are basically the same is on the way they are recording the light that is coming through the lens. So each lens, each camera is sensitive to a very restricted range of wavelengths. Basically, they are like within the visible spectrum, like sensible to the blue, green, and red color, but also it can be other lenses are more sensitive to the UV light and infrared colors that are outside our visible our view. Okay. Also, usually the multispectral images has a panchromatic camera that is exactly the same that you are using every day, taking pictures, photos with your mobile. Okay, this is just an example. Obviously, the output is not this rainbow assemblage of photos, but it's something more like this. So this is a comparison between panchromatic, so a visible light and normal camera images, and an infrared photo. The main difference you can see here, they are extracting different kind of information. And the simple example is my skirt that is completely white in the infrared and has some drawing on the light we can see from that photo. So basically, the way the multispectral camera is recording images is taking all the photos from each of the cameras and packing them together, building a block. That block, represented from the drawing in the middle of this slide, is a line, and that means that each pixel is a line too, and that means it is recording the same information, like the different information from the same scene within different ranges of wavelengths. Each pixel has a number on it, and basically we can plot that like column of numbers. If you assume that those numbers are also related to a specific object in the scene, we obtain what we call the spectral signature for each object in the scene. That means that, for example, here, the green signature that has these up and downs correspond to vegetation like a tree. The other one, the blue one, can correspond to a cloud. That means that all the pixels that are very close to the known signature are probably the same object in the scene. So if I know that in a scene there is a fossil and I can target it and I can extract the spectral signature of that specimen, I can plot it and I can compare it with all the signature in the same scene to try to see which of the pixels are more closely related to my signature. And that means finding new fossils. Okay, now that we have these main ideas in our brain, let's spend some time talking about we all know, we all love that are fossils. So I tested my hypothesis, my method, to these three localities: the petrified forest in Arizona, the Pisco Basin in Peru, and Wadi El Hitan in Egypt. All of them has three main characteristics that are the basics for run this analysis. That are large fossils that are exposed on the surface, and there is no coverture, so they are basically desertic area. I use two satellites, images from two satellites that are the WorldView 2 and the WorldView 3. Those are the information for the WorldView 3, but basically they have a resolution in the panchromatic between 30 to 50 centimeters, and they can reach 1 to 2 meters resolution in the multispectral, in the block we were talking of images we were talking about earlier. And both of the satellites has an orbit that is over 600 and 700 kilometers above our head. So the petrified forest is a Triassic deposit characterized by fossil logs that were buried in a river stream or lacustrine stream with some sort of volcanic ash influence and fine sediment. That means that water was rich of mineral, mostly iron and manganese, and those micro minerals were able to mineralize the logs. They maintain their macro structure, and other researchers earlier than me recognized two types of fossilized log. The ones on your left is a brownish log that is less preserved. It is fragmented in pieces, but it preserves the inner structure. When you cut the mineralized log and you see it through the microscope, you can actually see the inner structure of the original plant. The other type of fossils are reddish fossil, and they look more better preserved, but when you cut them and you look at them at the microscope, they lost completely the inner structure. Anyway, those are similar fossils in the same region, and I'm going to try to map both of them with the same classification. Just a notice, just information, the original plant was able to reach over the 60 meters of vertical development, and that means the fossils on the ground are huge. You have more than 10 meters sometimes of preserved fossil logs. Also, in the sea, that means in the Petrified Forest National Park, we had to consider two things. One is the vegetation coverture, and the other is the topography. Regarding the vegetation, it's a grassland. It's very dry, but vegetation is more or less growing here and there with spotted places. Regarding topography, even though the fossilis, the locality has up and downs, those are not big jump, and so we consider them not interfering with the classification, and so we consider this region as a mostly flat region. That is good for the classification, but because that means there is an homogeneous surface. So this is my worldview to imagery taken from the satellite. And as you can see, you can recognize stream beds and also the road going from north to south, cutting the national forest. But other than that, it's a patchwork of different lithologies, and you cannot really recognize even a geological division of the area. This is why I focus my attention to this specific place that is called the Crystal Forest, where there is a trail where tourists can stop and walk in through the fossil logs. Because it is a national park, it is very hard to obtain the permission to walk outside the path. And for the specific purposes of this project, of this test, I needed to have a clear idea of the fossils, of the real fossils that are exposed on the surface. This is why I decided to run the classification on this region, where I can actually walk, and I walked through the path, mapping where the fossils are. So when you are zooming and trying to extract the spectral signature from the specific area of the crystal forest, you can see that the trail, the anthropic artifact, like the road, the parking spot, is well recognizable. So you can really cut off what is the anthropic artifact, the asphalt on the scene. Also, when you look at the bare soil, you have some sort of distance between that and the other two objects that are in the scene. The two main objects that are kind of matching are actually the real fossils and the stream beds. That is partially a bad news because we need to classify, to match all the pixels in this scene to those spectral signatures that are our target, our end members. And that means that it can create some sort of confusion. But we see how the classification went. So I ran, obviously, multiple classification of the same scene using different algorithms. There are, I don't want to say 100, but more than 10 kind of different algorithms that allows you to clusterize an image. For the purpose of this talk, I decided to just show you one image that is the results of the maximum likelihood classification. All the algorithms are more or less trying to reconduct, to clusterize all the pixels in the scene, the close to the to an object that you already recognize on the scene. I use as a target the two kind of fossil logs, the ones that is reddish and brownish, and also the bare soils, the stream bed, and the anthropic artifact, like the ones I plotted in one of the last slides. So this is my first classification, and you can really see that there are some red pixels where the fossil should be, but there is some sort of mixing between the potential fossils and the trail and the bears and the soil. That means I needed to filter my map using standard method to delete or to recognize vegetation. The ones I use is the NDVI. It's a standard method to recognize where there are grass, there is grass, or there is some sort of vegetation. So with a subtractive layer, I just remove the trail and the vegetation. This is those are the two masks I use to filter and to clean the first map, and this is my result. So the result is composed by a cleaned map of red pixels that should correspond to my to real fossils on the ground, to real fossil logs on the ground. So if you don't have any other way to verify your map, you can take this map, the ones on your right, and go to the field and actually try to avoid places where there is no evidence of red pixels and focus your attention on the places where red pixels pop up in your classification. Because I was testing the consistency of this method, I needed a control map that was the actual map of the real fossils on the ground, the real fossil log on the ground. I created that map using Google Earth because I knew how was the ground. I knew where the fossils are. This process was time-consuming. It required me more than 4 or 5 days because it was multiple verification on the ground. And there are some sort of issues related to subjectivity because I was the ones running, delimiting the polygons. And as I already said, some issues related to data sources, to the use of Google Earth. Anyway, when I matched the two maps, you can see that the estimated map in red has a good match with the control map, the true map of fossil log that is shown in yellow. The verification of the map, the matching between the two maps, allow me to verify two main things. First of all, we reduce the region to be surveyed in order to find fossils of just 10% of the entire cluster forest. And that is a huge improvement because that means a hypothetical crew can spend more time searching where estimated fossil were and not just randomly walking through the surface. Secondly, we reducing so much the area still allow us to find 10 to 20% of the fossils that are exposed. So the first matching was giving me an idea of 10, 20%. But that was considering just the area because pixels are not objects, but correspond to area. when we consider objects instead of pixels, instead of area, and so we say that each group of yellow pixels are just one object in the scene, the percent of true positives, so true fossils detected with my classification, went up to 60%. It depends on the classification I use. But when I also filtered the control map with the minimum resolution of the fossil, we don't have to forget that the multispectral images has a ground resolution of 2 meters. That means that each pixel has a side length of 2 meters. That means the area within each pixel is 4 square meters. And that means it cannot detect fossils that are smaller than that size. So when I filtered the control map, deleting all the polygons that are under 4 square meters, the matching between the two maps went up to 80% and more. That is a very good result. And so we obtained 2 good results. We reduced the area to be surveyed in order to find fossil, and we obtained a good matching between the control map and my estimated map. That means we save time on this hypothetical crew, and we could spend better the money, reducing the cost related to the fieldwork, and reducing the risk related to the fieldworks. Let's jump to the second example. I'm trying to go faster on the last 2 examples because their results were more or less similar. So the Pisco Basin is a Miocene deposit, is where whales, baleen whales, mostly baleen whales, are exposed on surfaces. And those are cetaceans, so they are huge animals. But this place can be really considered a Lagerstatte because also otters, seals, and birds were discovered in the region. And so it gives us a real idea of what was the entire fauna around the region during the Miocene. So the most iconic representation I could find of this one species found at the Pisco Basin is the one on your left, that is the Leviathan. The Leviathan is a related group of sperm whales, and they were these huge animals still having teeth and probably eating other whales because they were very big. And actually the skull of the Leviathan was found at the Pisco Basin in a specific place at the Pisco Basin, and it is today exposed at the Paleontological Museum in Lima. So the deposit was a marine shallow water, accumulated on a marine shallow water, and where the animal died, and they were included in, some of them were included in a dolomite cocoon, and that preserved the skeleton to be completely avoiding a complete decomposition of the skeleton and preserving the fossil until today. But that means the fossils have more or less the same color of the background. If you can see it on the image, on the photo on the right, you can see the first view. So the closest view is the skull, and more or less the entire animal is more or less beige or some sort of similar color between the skeleton and the matrix. The region is completely desert. There is no vegetation, with very few exceptions. And it was impressive when I was there because you couldn't even see insects. at the base camp, searching for water or some food. There was no sign of any kind of life. That is kind of impressive, really. And the topography at the Pisco Basin is different from the ones we saw at the petrified forest because it is represented by terraces and hills. So the jump from the valley to the top of the hills is over 30, 50 meters sometimes. That means you can kind of realize that when you take a look of the satellite images, the ones on your left, when you see the circles spread over the entire image. So all the circles are the top of hills. When you zoom in on the square region where I was testing the method, you can see some interesting things, like the trail where the cars were driving. They are completely well recognizable from the satellite, and that's a very good information if you consider that this kind of resolution is the same throughout the entire region. And also you can see the fossils that are in the circle on the top of the right image. The problem here is that previous researchers clean up the surface to obviously analyze and drawing the fossils. That means they created some sort of aureola around the skeleton. And that's bad for my classification purposes, because that means, because I'm searching new fossils that are not clean, that has no aureola around them. And that means that the algorithm is confused because of this presence, let's say, of a different signature from the ones the algorithm is expecting. That means you can see the same object in the scene, even when you are considering the low resolution images. That means the multispectral images, the ones I use to classify the scene. And that means when I try to clusterize different objects in the scene, I obtain a classification that is closer to a geological map or a stratigraphical map instead of the classification of the true fossils, of singular fossils. And this is particularly true for the region I was interested on when you compare my classification with the preliminary geological map published by Bianucci et al. In 2016. On that map, you can see all the little drawing that are actual fossils on the ground, so you can realize pretty clearly the quantities of preserved fossils that you can find over there, and they are still there, and they should be monitored closely. But my classification didn't work in this case. Let's go to the last example, that is Wadi El Itan. It's an open-air museum, and Wadi El Itan means the Valley of Whale in Egyptian, and that locality is more or less represent the same characteristics of the Pisco Basin, more or less. Marine mammals, big archaeocities that are a sister group of modern cetaceans, and they are completely extinct, and they are there is a topography that that should be corrected when you try to classify the images. And in particular, the archaeocities were animals that could reach 20 meters, starting from 5 meters of length. And they are basically, the locality per se was listed as UNESCO heritage since 2005, because the presence of more than 500 of skeletons over this surface kind of testify the evolutionary trend of modern cetaceans starting from terrestrial animals. The Basilosaurus, for example, still has teeth, and some of the characteristics of the postcrania are showing a relation with terrestrial animals. So this is the image I used, and the museum is located on the southern part of the image. Again, here, like at the Pisco Basin, you can recognize the museum built over the best preserved fossils of the region. The base camp recognized with a little star on the left, and the trail where cars are driving to show the tourists the location of the fossils. When you zoom in, you can again recognize the trail and kind of recognize the place where the fossils are exposed. Again, because the color of the skeletons is so close to the matrix, to the background, it is very hard to be able to recognize the fossil. When I say color, I'm meaning not the color in the visible light. I'm meaning the color from the UV, the ultraviolet light throughout the near infrared. Also, a final thought about the Wadi al-Hitan. Unfortunately, our communication with the Egyptian responsible were interrupted, so I couldn't look further this locality. So some final thoughts before your questions. The main question is that possible to find fossils from space? The answer is yes, with some constraints, with some limits. The first one is the size. We are looking for fossils that are big. The second one is the color, and the color is a representation of the mineral content of each fossil per se and of the lithology around the fossil. But the good news is that the classification, the method I'm applying is completely independent from the taphonomy, so the macro group of the animal, the skeletons that are exposed on the surface of the fossil logs in this case, and it is also independent from the geological age that opens to application for example, for dinosaur localities and other sorts of vegetation localities where we can apply the same method. It also can be improved with using drone, for example, that increase the resolution on the ground, or radar data instead of optical data. That means SAR instead of cameras, multispectral or hyperspectral cameras. Unfortunately, hyperspectral cameras are not loaded on a satellite yet, so we are waiting for that. So at the end, the potential to map fossils on the ground, singular fossils on the ground, is very high for places like the petrified forest, is very low for now for Wadi al-Hitan and the Pisco Basin, so places with too many similitudes with between the fossil and the matrix. But we are still working to improve the method, and we are trying to apply some artificial intelligence on the method and other sort of classification. With this, I want to thank the European Commission that is allowing me to run this this project, and of course the University of Venice and the University of Oregon, where I'm learning so many different things. And those are just some platform and softwares I'm using to run my analysis. And thank you all that are still online listening my presentation. I'm open to questions. Thank you again.
Thank you very much, Elena. I have to say it's lovely to see drones being used for something other than dinosaur footprints, which seem to be like the standard thing that was large enough that you could see from the sky and plot interesting patterns from. So that was really fascinating to see that. We're now open for questions, and I've one from Femke, who asked if there are any ramifications in terms of any legal issues that you've run into, because obviously drones are very well, they're not so popular in some areas of the world, and I guess that could be a problem.
So yes, for example, in Peru, you cannot move a drone that is brand new because they suppose you are going to sell it there. So my drone has some sort of bad impact in the past. So they check it, they control the drone, and they realize it was used. So I was ready to go. So the problem with drones is that it can fall down, it can crash, and pieces can spread everywhere. It can explode, literally. And so a lot of countries are now restricting the use of drones because the general idea is the use of drones for military purposes. So if we don't disconnect those two ideas of a drone to be something dangerous, we will encounter many, many issues every time. Nothing that we cannot resolve. Most of the time, you ask for the permission and you can get the permission wherever you want to go. I know some researchers are moving drones that are small enough to pass over the control, but that creates issues when you want to publish videos or something like that. I also have the US license for drones, and they are more or less the same in Europe and the US. The main thing is that you have to prevent a crash and any risk for the land where you are flying and for people. Those are the two main things. And then it requires some time to get the permission from specific place where there are other aircraft flying, like airplanes.
Yeah.
But that requires time more than straight no, it's not possible. Usually they need to check and to restrict the time when you can fly and the altitude and so on.
Okay, I'm guessing from what you've seen, are the restrictions legally getting easier or more difficult as time goes on? I would sort of guess the latter, but I don't know if that's been your experience.
What did you ask? Sorry.
I was just wondering if the legal restrictions have been getting more difficult through over the last couple of years, or as opposed to getting easier because.
So I'm guessing the restrictions will be stronger, but the technology is running faster. So we are getting to a point when a drone can fly and decide to avoid objects. We have drones that even if it is very windy, they can control their position. We have drones that control the battery over the flight, so they recognize if there is any issue and they can fly back to the main point or just land where they are. So the technology is running fast. The problem is when you are using drones, you realize the drone is not the main thing. Searching for fossils, you are not really interested on the drone per se and how it works and what are the restrictions. The main thing is the camera that is on the payload. So the characteristics of the camera are the ones that are giving you the output, the map, the orthophoto of the scene. And that means you want to have the best camera for your purposes. You don't want to have a camera that is a fisheye, for example, because that creates distortion you cannot correct once you are back in your office. You don't want to have, you want to have a camera that that collects the images in a way that you can work with them to create a 3D model of the surface, and so on. The best thing that is already on the market, but is so expensive that it's a big responsibility to move it on the field, is to have a good drone with an hyperspectral camera. I know some people that has that technology. I'm not taking the responsibility to ask them to move that drone in a desert. I'm not feeling sure about that. If somebody has more, like, is braver than me, open to do it. I'm excited about the results.
Okay. Perhaps in that theme, a question from Aidan. How far do you think this technology could go in the future in paleontology?
So if you're speaking about satellites, again, the hyperspectral cameras, okay, the difference between the multispectral and the hyperspectral is that while the multispectral has like 8 bands, but they can have up to, let's say, 20, I guess. But the hyperspectral has 200 layers. Wow. So they are recording, so the spectral signature, instead to be peak and down, narrow down, you have a curve that is giving you more information about, a better information about the object. So you can distinguish the two objects, even though they are very similar. With a curve, you have a better definition, a better resolution of the signature, and you can distinguish them easier. So the best thing, I'm waiting for that, is to have hyperspectral camera on satellites with the same resolution, of course, hopefully, of the multispectral. That allows the researchers to really monitor vast area, just clicking or just creating coding that run the analysis automatically. Recently, there are some development in the SAR technology that has similar resolution. It's not optical. I never worked with that, so I don't know exactly how it works, but that can be something in the very next future, next few years. Yeah, I don't really like drones that fly from here to another country, and I don't think they will be our future, or they will be available for private researchers, because there are issues. In this case, there are issues related to the control of those drones, and absolutely the right of people of not having drones flying over their heads if they don't feel safe.
Okay, I guess that kind of partly also answers a question from Jesse, which was how do you tell a fossil from a rock in terms of the level of spectra. Clinton was asking, do you think the use of low sun angle images, bringing out the shadows, might be help in picking out at least some of the larger fossils?
That's a good question. So it's a new field, and we are testing the method in different with different challenging with different issues, let's say issues for each locality. So shadows are good when the fossils are big enough to cover more than a pixel. That's not correct, because even when you have fossils that are less than a pixel, but they are mixed with the shadow, maybe their spectral signature is something significant. The shadow can be helpful. It can also be distracting, because when you have dark pixels, they tend to they are recognized as an object, whatever object originated them. So if also a rock create a shadow, probably that shadow is very similar in spectral signature to the ones created by the fossil. So it really depends. The thing we are seeing now is that it really depends on the locality you are dealing with. I recognize this similitude among between the two marine localities, but we need to dig deeper on this before to be sure, of course.
Okay, I think perhaps related a little bit in terms of comparison of nearby pixels. Harvey asks, in your presentation, you talked about traditional clustering algorithms to identify likely fossils. Did you look at using convolutional neural nets to extract features for classification or to perform the localization and classification directly? It would seem that considering nearby pixels might help distinguish fossil deposits from geographic features such as streams.
We are trying different methods. We are trying neural network. I'm trying object-oriented classification, and so on. All of them are very preliminary results. For now, I don't see a real improvement of the output from the maximum likelihood or the spectral angle mapper classification. That's the other one I'm using. Spectral angle mapper classification, and it's a matter of time and trying and see what happened. The neural network can be something. It was applied to searching for outcrops and improve the, for example, the comparison between that one and the unsupervised classification, but we are still running the analysis from them. I'm totally open to collaboration if you want, if you want to try.
Excellent. No, that's it's very good to know. Let's see. I mean, similarly, Clinton was asking, considering that these large fossils physically stand out above their background, would satellite altimeter data and pattern recognition be of some use?
What did you say? Sorry.
Satellite altimeter data and pattern recognition be of some use.
Yeah, sure. As I mentioned, this is a completely new point of view. And I focus my attention of the fact that the resolution now allows you to reach the point when you really can classify singular pixel or singular fossils. But absolutely, this is another possibility. Most of the fossils that we are dealing with, because they are large, they are not moving, for sure. But repetitive imageries can be a very important thing when you want to monitor the land, preventing black market, preventing fossils to be stolen. And that can be very important for places where it is a big thing. for places that has no other tools, no the support, the financial support to control the land in this way, because we are talking about thousands of kilometers, of square kilometers.
Okay, a question from Alison. Could you go over some of the minerals you're looking at again in these searches, and what's the sort of mineral signals you're considering using in the future?
Okay. In the case of the petrified forest, the fossilized logs are rich in iron and manganese. I also try to extract the spectral signature from the matrix, from the background of some of the localities, not specifically from the petrified forest, because as I mentioned, it's a national park, so you cannot take anything from there. And so we are trying to recognize difference from the spectral signatures that are from specimens we are analyzing in the lab. Also, that is kind of confusing for the moment because we are trying to avoid to destroy the specimen. So sometimes there is like a cortex or a manganese accumulation on the surface of the bones, not only on the fossilized logs. If any of you has some familiarity with bones, fossil bones, most of the time you see they has accumulation of manganese, and that can create some sort of confusion between the matrix and the fossil. I'm not actually looking specifically at what kind of mineral are in the fossil or in the matrix. I'm looking specifically on the spectral signature because it's easily extracted from the fossil and from the scene, and it is also not destructive. You don't need to destroy the specimen to obtain the spectral signature, and that's pretty good. It's a good news for the fossils that are in museum and so on. For the specific case of the petrified forest, other researchers analyzed them and they found rich content of iron and manganese.
Okay. One final comment, I think. That's actually from Sean, who wanted to say thank you. He's doing his master's with field-based remote sensing and drones at Dinosaur Park, and he's excited to share his findings later this year. So I want to thank you very much for your talk. So
absolutely
nice.
Thank you.
Yeah, if there's any other questions, I'll take a couple of minutes to say next week's presentation, which is also sponsored by the Royal Tyrrell Museum Cooperative Society, will be from Professor David Pauly, former president of the Society of Vertebrate Paleontology. And he'll be talking about paleontology in US national monuments, particularly in relation to the legal case concerning one President Trump over the last couple of years. So that would be an exciting one to tune into next week. So can I say, if there's not any further questions, I'd like to thank Elena again. Thanks very much for doing such a fascinating and very different approach, but clearly there's a long future ahead for this particular use of this technology in the science, and it's really exciting to see where it goes next. And with that, I'll say thank you very much for attending this presentation, and hopefully we'll see you next week.
Thank you, everybody.